Good morning, everybody. In the last class, we were discussing about the somewhat introduction to machine learning. We discussed what is it that this machine is going to learn, what for is it going to learn, why is it going to learn, or how is it going to learn. Okay, that is what the content of this course is all about. And what else did we see in the last class? We have seen a big picture of machine learning in general. Of course, you can interpret many of those inferences to machine learning as well as deep learning or data science are all these relevant, somewhat relevant areas, right? And we have also seen to an extent how can we distinguish between machine learning, deep learning, and other relevant buzzwords that we keep hearing. This is what the example we have seen in the last class on what could be the role of machine learning, assuming that do a classification of, let's say that's a assume that it's a benign tumor and malignant tumor, and mean and variance values of the image can uniquely this malignant versus benign tumor, or can uniquely distinguish these two parameters are good enough. So that if that is the assumption, then we have seen that maybe, yeah, this can of course can have some values here, some values. So you have some training data set essentially. So from the training data set, by annotated training data set, by annotation you mean you know the ground truth, whether to which class it belongs to. Assume that you have some 100 annotated training data with you. Let's say you use 80 here, and then the rest 20 to test your thing, or later even if you do not know ground truth, you can still use that. So with that, what you will do, you will figure out for each of them what is the mean and variance values. Okay, mu is the mean, you could think of. Sigma is standard deviation, if not variance. Sigma square will be your variance. You plot it, and if you see them into two different clusters, then you could come up with a line separating them, right? So that's how you do it, right? Then I was talking about feature here. For example, in this example, what are the features here? What are the features that we considered here?
Mean and variance.
Correct. Mu and sigma are standard deviation, are the features that we have considered. Each one is a feature. The whole thing you call it as a feature vector typically. This is what you call it as a feature vector. And of course, this is the feature vector representing your sample. Suppose you take this image. Okay, this is sample one. This is your sample one. Similarly, you might be having overall 80 samples, out of which, let's say, some 40 or 50 belong to one class, the other samples belong to the other class. So that we represent as a sample. And feature vector now can be seen as a random variable. To be more precise, it's not just one variable. It could be a random vector drawn from the sample space. So when I'm saying sample space, you have multiple samples there. So from that, the sample also is one random pick from your entire cluster. That's how you can look at it. Now, you might have already heard these words, supervised classification, semi-supervised classification, and unsupervised classification. So I think we also very briefly discussed or touched upon, maybe I am not very sure. Can any of you shed light on that? How are they different? Supervised, semi-supervised, unsupervised.
Sir, in supervised training or learning, what we have is that we have the output labeled as well. Like we
Right.
know what categories they belong to, and in unsupervised, it is not exactly clear what categories they can belong.
Very good. That's all. And semi-supervised is part of your samples. you know the output. For the rest of the part, you do not know what is the expected outcome, or to which sample space or which class it belongs to. Maybe we let us use the word class here, to which class it belongs to. Okay, right, very good. So those are the three classifications. Yeah, that's anyway further I think that's good enough. Okay, so okay, this I had made. And now let me put the whole stuff here and tell me. Here we are trying to see what could be the overview of a classification system we are taking a look at. Well, although we are talking about a classification system, for any other application, for example, a segmentation, only one block would be varying here. For example, when instead of a classifier design, you have a segmentation design here. Or you could take any other application. It could be denoising you might be doing, not just segmentation. Deblurring you will be doing. So how do you do that? So again, to get a picture of it, let us consider a particular application. Since our course is about ML for image processing, let us consider image processing as itself as our application here. So what is the whole process that happens here? There is a physical scene and a physical phenomena to which you are capturing an image. So that is where your sensor is basically your camera is your sensor. And as an output of your sensor here, so I'll just draw in parallel for a image processing application. And what you get out of it is an image, for example. Well, again, this is one way of drawing one possible representation. You could always think of it in a slightly different way. So typically what you do is you would be doing some pre-processing of your image such that it's more suitable for the type of task that you want to perform. So, well, that you could, if you want, you could write here as some feature or observed data. So what you have here at the end of that is you have some data. Observations are there. Image is nothing but I could write it as observations. Okay. Then you could have, let's say, a pre-processing module here. There could be a pre-processing module. And of course, in your diagram, if you want, you could consider this as a part of this diagram, this part itself, when it's a part of your sensor. It's up to you. Fine. Okay. So after that, what do you have? You have, let's say, an image where you pre-processed and data is ready. And from that, let's say, just let us go back to the previous application here. What is it that you did? You have extracted from this data two features, right? The mean intensity and the standard deviation of the intensity. So similar job you can do here, and that's what you generate some features. Feature generation, you have it. Okay. Then what? Not all features that you generate might be too many. For example, mean and sigma is one, but I could also in fact consider all my pixel intensities as also as features. You will see that shortly in the coming classes. Sometimes these features are too high. So from this, there could be instances where you want to do some selection of features. Okay. So only those which are very critical to you. So again, I am writing it in general. As I mentioned, you could always modify. For example, this feature selection and generation could come together. Let's say, consider the case of Fourier transform. When do you think representing an image in the Fourier or a frequency domain than in the spatial domain could be more useful? Can you think of some scenarios where, for example, after pre-processing, I got an image here. But at the time of feature generation, I would rather move to a frequency domain rather than the spatial domain. Can you give an example for that? For which kind of filtering you would prefer Fourier domain rather than spatial domain? Which kind of scenarios? I give you a signal. I then which could be some specific examples where you filter that signal. Forget about image, just take 1D signal. What are the scenarios under which you would prefer dealing with that signal in the Fourier domain than in the spatial, in the time domain? Let's say I'm just even a simple 1D signal. Let me give another example also. Assume that my fan is rotating here. Okay, right. This is I'm under a noisy environment where my fan is rotating, or somebody outside my room is doing some job like cutting and all, okay, with a machine, which is giving, let's say, a creaking sound, okay, very high frequency sound. So I want you to now perform an enhancement to the speech signal. How do you do that? It's a 1D signal. How do you do that?
Sir, noise removal, right, sir?
Yeah. How do you do that?
Yeah, we'll
Ah,
pass through low pass filter since we know that we have an idea that sound produces high frequency noises.
very good. Very good. So low pass filter, can you give me an example of a low pass filter? So if you have a high frequency, yeah, one of you had said it correctly, sin x by x, sync in time or frequency?
Time.
Time. What is its equivalent one in frequency?
It's a rectangular function.
Yeah, rect function. So what will it do? Only in the frequency plot, when I have here, let's say, let me call this as omega, or maybe not omega, let me call this small omega here. I consider, let's say, I should have ideally consider DFT, but let me consider DTFT. Okay, so DTFT, what is the range? I just want to ask you.
Minus pi to pi.
Right, very good. I could, should I consider only minus pi to pi, or 0 to 2 pi also can I consider?
So it can be any range of pi to pi.
Good, good. So this is a rect function here. Okay. So then what will happen? Any higher frequencies here will be eliminated. So to do that, I would prefer bringing that signal into a frequency domain signal. Okay. So anyways, coming back here, this is one example. When in terms of frequency, you know it. Let me give you maybe another example is, have you studied anything about discrete cosine transforms and other things where you could use those transforms to compress your signal also, or encoding you could call. So an image also can be represented using this discrete cosine or all these transforms, very similar to Fourier transform, but you might be using just the cosine based approach, cos omega t plus j sin omega t kind of stuff, not exponential, complex exponential as such. So sometimes your signal can be more compactly represented when you make a transformation to your signal. That's the basic take home message here. So that is how you would be generating your features there. Okay. For example, maybe going to a Fourier domain would represent your signal in a more precise way. That is one instance where other domain could come into picture. One of you rightly mentioned, performing even image pre-processing would sometimes be much simpler or computationally less expensive. If you go to Fourier domain and do it, that's another scenario, right? And third scenario is, even for this pre-processing, suppose when I have a noise here, when my noise is lying here in my signal, in my spectrum, applying a filtering in for taking that signal into Fourier domain, analyzing it there, applying it a filtering there, and bringing it back. That's what I mean by feature generation. So what you could perhaps will be doing is, you would be going to a Fourier domain and representing is also one type of feature generation. Okay. And of course, there are ways by which you could eliminate some of them, where you would figure out that they are not very important. Okay. So that is where you could have a feature selection, and finally here comes your classification module or segmentation module or whatever. Then you have on a annotated training data, for example, you could have, yeah, by the way, as I said, this is depending on your application. Sometimes pre-processing, feature generation, selection, one of these modules may not be there, or one would be done combinedly with other things. So there are all possibilities are there. This is just to get some idea here. So here you have a physical scene that or a physical phenomena there which you want to observe, and you have made some observations, and this is the process. And you might be in the whole process, you get some output at the end of this. Then what you do, you may tune any of these, this output of this evaluation you might give to any of these modules, and you modify that again, any of these modules, look at the output, and then if it is improving or if improved, you keep it, or if you expect it to be further improved, you further fine tune it. You could do it for in any of these sections. For example, it could be this feature selection, you drop one feature, system evaluation, you do it whether it improved or not. If not improved, if it is giving you still the same accuracy with dropping a particular feature, you drop it. So all these are, this way you could do it. Okay. And of course, if there is a feasibility, even your acquisition also could leverage from your system evaluation. Again, as I said, it depends on your application. So this is, and if you look at the contents of our course, it is mainly would be in case of you have an image. So you could call this pre-processing or feature generation. These two is where the image processing module would chip in. So it will tell you, you should be able to do some amount of processing, pre-processing required, such that it is more apt or more fine-tuned or customized to your application. That's what we would be studying after this shortly. So we will start studying that. And this could also be, we will also study at least one or two, at least I would discuss here some features. Features could be one feature to begin with, or the pixel intensities themselves are the features. But when you see an image, you will shortly see that there are other features also, which we will come to that. That's what we will study here. Okay. And feature generation, maybe he's still here, some advanced means now no more, still the classical, some of the features I would talk about. And after that, we will go to this classifier module, where we would study first a probabilistic approach for performing classification, Bayesian framework for performing classification. And after that, not necessarily these classes should be modeled as a in a probabilistic approach, but rather you could also, as I was also mentioning in the previous lecture, you could directly come up with methods for designing these boundaries between the classes. Okay. Say, for example, this is called as a linear boundary here. You could see a line is representing. Of course, if you have multiple features, you call it as hyperplanes there. Okay. And assume a case where, for example, it need not necessarily be this way. You might be having a boundary like this also is possible, where here again you have, let's say, benign tumors. Okay. Or sorry, the other way around. These are malignant tumors. Okay. This is benign tumor. And the boundary separating them need not always be linear. So we start with probabilistic models, a probabilistic modeling of all these classes and everything in solving this problem. Then linear classifiers, then nonlinear classifiers. Again, linear classifiers means perceptron or neural networks would come into picture there. Support vector machines we would be learning that. And then nonlinear classifiers, there are ways by taking multiple perceptrons and combining them in a particular way, you could even deal with the problems that have this nonlinear boundaries. You would also see that even with a probabilistic model, we can design or distinguish classes that are separated by a nonlinear boundary. That also you'll see. These, by this, we would be covering the first three parts of supervised classification, all these things. Then we will go to unsupervised classification, where we know that these are the features that distinguish, but we do not know to which class it belongs to. So then you look for some clusters. Where can I form clusters? And accordingly, you will be doing it, which falls under unsupervised classification. We will at least discuss their k-means clustering method and maybe mean shift algorithm for performing the clustering. And we would also discuss something about these feature generation or selection, where, let's say, PCA based methods, there are certain things which would actually bring in a dimensionality reduction. See, for example, if there are only very limited frequencies in your image, the moment you represent it in Fourier domain, for example, 2D Fourier domain, the number of features could come down there. Few number of frequencies are good enough to represent your image. So that's also comes under dimensionality reduction problem. So feature generation, feature selection, you could put either or in between somewhere, where too many features, you would come up with a transformation that reduces the number of features. We are going to study some such methods also. And after that, we will go to, let's say, a overview of convolutional neural networks. And then we would see applications, as I was mentioning, in the whole process. As and when the context arises, we would see definitely a classification problem, a segmentation problem, denoising problem, and also perhaps other things like deblurring. So this is roughly the details of the proposed menu for this course for the semester. So any questions? So with that, the introduction about this course is done. And now I'll start with a brief introduction to image processing now. Spend a couple of weeks on getting some basic image processing methods, understanding and knowing some basic image processing methods. Okay, so this is where now we are moving from introduction to the course to introduction, one of the modules, that is image processing. Okay, any questions, comments, or doubt so far? I think this is the right time to pose your any queries.
So I've got confused about what is this pattern here.
Yeah. See, this again, these are the pattern is something I purposefully did not mention it as a pattern. What the author of this book, Theodoros, the textbook that I am referring to, he's referring that there is a pattern into it, and from that pattern, to capture that pattern, you are taking the sensors. That's what he meant. But I would rather prefer rephrasing it in a different way, which which I was mentioning in my previous class as well, where here there is a physical phenomena or an object you are observing, and you are trying to characterize your pattern through this whole process. That is how I put it. I will not put there as a pattern, because for me, the way, again, as I said, there are different ways people would define these terms. I would rather, what I call as a pattern would be a unique signature. If we talk the signature in terms of classification, for each class, or a unique signature that you are going to explicitly or implicitly learn, which distinguishes different classes. That's how I define pattern. So that will not, good that you noted it and raised that question. I would replace that word with something else. I will not use the pattern word there.
Okay, sir.
Yeah, good observation. Yes. Any other question? let us now enter into the subject now. So the first question I would start asking you is, when can an object be imaged? I want to take an image of an object. When can, I'm not asking you how, I'm asking you when can an object be imaged? Don't tell me when I have a camera. Tell me in more conceptual way, when is it that your camera can image an object? If I can't see also, I can do it. You know IR cameras, right?
Yes,
They
sir.
do when it is in the infrared region, which we cannot see, you can take those images.
Sir, when the illumination or the radiation from the object is greater than the threshold level of the sensitivity of the sensor, then we can probably
Sensitivity
image
is
it.
different. See, I may be, that sensitivity could be for a particular range. So it's not exactly sensitivity. I know what you want to say, but the way you formulated is not appropriate. What you thought was correct, but the way you put it is not correct. You cannot see everything. You can see only that which falls into the visible light spectrum, which your eye could see. Okay. Can you see everything in the visible light? So that's first thing. Okay. That is the first boundaries we have. My next subsequent question is, can you see everything that is under visible spectrum?
No, sir, then the resolution will come into picture. Whether can our eyes resolve that image? If it is too small, then we can't see it, though it may be reflecting visible.
Very good. Very good. So these are the two things that you have to keep in mind. First thing, you should have a sensor that is capable of detecting energy radiated by that particular band of electromagnetic spectrum. We can see visible light. If you are going into, if you have seen any of X-ray imaging is there, I'm sure you all had X-rays sometime, chest X-ray or something of other form. I'm sure every one of you would have had it. So there, we cannot see those X-rays. What is there inside, you cannot see. But of course, when there is a sensor which is sensitive to the electromagnetic spectrum of X-rays, when that got exposed to it, you can see it. Correct. So very important thing is, it is not enough. Should it always be a reflection from the object? Can you not see something which got refracted? If it is falling on eye, can't you not see it? Should it always be a reflection? It could be the other possibilities also. So what is more important thing is, refraction also you could see at the end, that light should fall on your eye, and that should make sense. But then you should have a sensor. Okay, our sensor is here on the back of your brain, where the signal is going there and getting analyzed there. So that should be tuned for visible spectrum we have. But when it comes to digital images, this can come from various spectrums of your electromagnetic spectrum, various parts of your electromagnetic spectrum. Second thing, light might be getting reflected from an atom as well. You cannot see atoms in molecules, and you can't see something. If you have some magnifying lens before you, you could see something which you cannot otherwise see it. So what should happen there? The wavelength of the electromagnetic wave is required to see and must be of similar size or smaller. Anyways, the wave, it is also about the wave that it is coming. Okay, the wavelength. So suppose you could always figure out, unless that intercepts your wave, the object size is such that it intercepts, unless and until that happens, you won't be able to see it, right? So, well, in case of imaging, it is not necessarily always a reflection. The light that got transmitted through the object. Refraction means there is some angle, isn't it? It's not that I'm talking about. You could have a sensor here, okay, where the light gets transmitted through this. I put some light here, or I could have a sensor here. For example, take X-ray image itself. There is a transmitter of X-rays. You stand in between. There is a receiver at the back, and those X-rays that got transmitted through your body is what it is receiving. So it is not always reflected, not necessarily always a transmitted light. It or reflected light, it could be transmitted also. This is what I want you to be aware. There used to be, I'm sure before this our cell phone cameras, let me call it that way, cell phone cameras are there. There is something else. People used to have the film and do it. Now, whatever we are getting images, we call them as digital. So when you consider this digital image, so basically you have two important phenomena in terms of your signal processing DSP you have studied. There are two important phenomena that are happening when an image, you are getting a digital image. Can you tell what are those two important phenomena?
Sampling and quantization.
Very good, very good. Sampling.
And quantization.
Very good, very nice. So there are two things that are happening, very, very important. That's why DSP serves as the signals processing, whichever you study, serves as backbone for many of these things. Without a proper understanding of this, you will not be able to do things in a very informed manner. Okay, there are two things that happen when a digital image is formed. One is sampling and one is quantization. Now, given these keywords, can any other one, I want others to give it a try. What perhaps could be the meaning of sampling here? Can somebody would like to give it a try? Just keep in mind how a sensor is there in a camera. What would happen there? The sensor cannot be at a single point. How you have it, this is again a cartoonized version of what a sensor could be. A rectangular array where the whole light falling onto, let's call it as a cell, each one as a cell, the whole thing as an array. All light falling on that particular cell, an integration of that is represented with some intensity value. Okay, this in background. Now tell me sampling. You are almost there, but now keeping this in background, now try to illustrate, try to describe about sampling. See, the whole thing here, see, the sensor is not a, you cannot make it is not a single zero area point, right? It does has an area. The whole thing you represented by a single value. So you have, for example, this might be, let's say, I don't know how physically it will be, 1 micrometer by 1 micrometer. Just for theory purpose, we consider it as 1 micrometer by 1 micrometer. So there is this whole thing. What you have there is integration over that area of 1 micrometer square, the whole intensity of light falling in that region, okay, is what is giving you one value. And that whole region of 1 micrometer square by 1 micrometer square, you have only a single value there. So that way, spatially, if you have a 512 by 512 image, you are discretizing, because you have only, unless you have a finite area, and also from physical manufacturing and quantification and all points of view, there is a limitation on to which range you could manufacture it, or to which range you can get it. So that is putting you the sampling. So when you say an image is of size 512 by 512, it is discretized with 512 values along your x-axis and 512 values along your y-axis. Is that clear? Is sampling clear? What it means in the context of an image? Now you try to answer about what could be this quantization now. Hope the sampling is clear now. So what about this quantization? Any thoughts about what could be perhaps this quantization?
Discretizing the intensity of the reflection.
Discretizing
the intensity or pixel value.
Right. Can you be more, can you give an example?
Like
Can
for,
anyone else slightly rephrase that?
So like for a grayscale image, we've already discussed that the intensity values are between 0 to 255.
Mm.
So, for example, in this first pixel that you have selected 1 micrometer by 1 micrometer, let us say that the intensity value actually came out to be high. Just for example, sir, let us say it came out to be 1.8. So it is being quantized to 2. And in case it came out to be 1.2, then it is being quantized to 1. So that is what is quantization.
Right. Good. That's good. See, let me slightly add to that. That answer is correct. 255 looks like, I think, other than those who already attended the medical imaging course, would look like a magic number. So let's not go into that at this point. Just after a few slides, I'll come to that. Assume that the highest I represent it as 1, let's say. Brightest one, I represent it as 1. So it's normalized in between 0 to 1. Now, I need to process this. Unlike a good old days film where anything could be there on that, here I have to store it. Store this image in a computer. Correct. So there is a precision, or there is a limit to which extent this value can take. For example, I cannot represent something like 0.123444444. It's going on. There is a limit to which I could practically store that. This limitation, you could more the number of digits that you take to store this image, the more precision you could store it, but there is a limit to it. Beyond that, you cannot have store it because you are digitizing it. So you are quantizing the value. So you would say, for example, anything, let's say you might have in terms of 0.1, you could do 0, 0.1, 0.2, and 0.91. Assume that. If I get 0.1234444 and so on, if I'm getting, I would consider it as 0.1 itself. So this is again, remember and comprehend, that is coming because you are digitizing your image. So this is the second important aspect of a digital image. Is it clear? Is quantization concept clear? Why it is coming?
Sir, so 0.12344 is the result of sampling.
No. See, it is, I'm taking this whole area intensity. Okay. So the 0 I considered as the nothing got there. It is the that intensity. This is some intensity I'm getting here. And this intensity, brightest, let us consider, is 1, and the lowest as 0. And each of these cell can have anything in between. But the moment I want to store it as an image, I need to store the intensity value of each of the cell of this array in a computer. You have int, you have unsigned character, you have a float, you have a double. This is how you store it. Suppose in a 32-bit machine, float is 32-bit. Double is 64-bit. Unsigned character is 8-bit. If you are using just one digit, 0 or 1, right? Since you are storing it, the intensity value, which is an accumulated intensity that you got at any of those cells, as you are storing it, it is from that this discretization, this quantization is coming. Sampling is, I want to see your, I want to store the image of your face. I store it as 512 by 512 image. This 512 rows and 512 columns is sampling. And in any of these 512 by 512 samples, I want the intensity of that, this is only like allocating space. What has to be there in that space? Intensity has to be there in each of these 512 by 512 pixels. The value which is there in that pixel, that is where the quantization part is coming. Number of pixels sampling is coming.
Got it.
Good. That's an important distinction which has to be clear to one and all. So any other question there? So here again, the same thing I am showing here with an image. Again, of course, the moment you are seeing anything on the screen, it is already a sampled one, and quantization is there, because after all, we are seeing digital images or digital video is nothing but one more sampling in time domain is also there for images. That's all. Even the speech you hear, the same thing is there. Okay. Anyways, coming back here, you consider one image is there here. When you say sampling, you are having its values at discrete points alone. And at this discrete point, it can have varying values there. You won't keep all those things, but you kind of round them off to a nearest value that based on the what is the maximum that you could represent. So this is where the quantization and sampling are coming. Okay, hope that is clear from this diagram also for you. This is just we are showing for one row of the image so that 1D signal is convenient to plot. So that's why it has been shown there. Another example here. Ideally, in this whole cell in an image, you could see there is some variation because you discretized it. Something like an average of that image is coming here. Not only that, this also you could see, while there is some variation here depending on number of bits you use to store that image, this also sometimes could fall into the same values. Okay, this again another way of showing this. As somebody who is dealing with images, we were already given the image. It's not, you are not focusing at the image acquisition level, but nevertheless, what would happen when you are downsampling the image? This has to be there on the back of your mind, because when you are doing this conventional convolutional neural networks, and downsampling is an inherent part of it, implicit part of it. So uh, up to which downsampling to what level could still help you in getting reasonable features, this kind of idea should be there. Of course, that comes from Nyquist theorem, and this depends on the content of your image. If not content of the image, the content of interest for you in that image, based on that this has to come. That is what would dictate what should be your sampling rate. Stop here, and we will continue this brief introduction to image processing in the next class.